we were in the true false. We have done this one, we have done this one, this one, this one. So now the next question in the true false. Optimum die angle depends on ideal, friction and redundant work. Right? So we have done it as equation also, we have done it as a graph also. So yes, this is true. Optimum die angle does depend on all the three parts of the force or work: ideal, friction and redundant. Let's now move to the problem type, right? The question 2. Rod drawing is performed on a cylindrical billet of annealed 304 stainless steel. Diameter changes from 10 mm to 8 mm at a speed of 0.5 meters per second. Frictional and redundant work together make up 40% of ideal work of deformation. Calculate the power required in this operation and die pressure at the die exit. So once again, this type of a problem we have done already in examples and homeworks and so on. So this should not be a big issue. If you want to do a good practice, then again, please pause my lecture, solve it once again as a good practice for the final exam, and proceed later once you have finished the solution very strongly in your own rough solution and so on. So let us see, as I always say, what is the data, knowns and the unknowns. It is rod drawing. There is a cylindrical billet. The material is annealed 304 stainless steel. Initial dia 10 milli, final dia 8 milli. Velocity of drawing 0.5 meters per second. This is important. Friction plus redundant work is equal to 40% of ideal work. What is the power required and what is the die pressure at the die exit, right? So writing this down, that these are the knowns and these are the unknowns, always makes a very good plan for your solution. So you want to find the power, but this is important that you see the total work will be ideal work, frictional work, redundant work. Ideal work, the equation is given. For these generally there is a difficulty, so they are saying that frictional plus redundant work is 40% of the ideal work. So the total work will be right, if ideal is 1, then 1.4 of ideal will be the total work. So this is it, and then power is to be found out. So as I always say, if power is to be found out, let us start by writing the equation for power and then start working backwards. So before we go further, because the material given is annealed stainless steel 304, so you go to the table at the end of the formula sheet, and K is 1275 megapascal, N is 0.45. So this you already have noted down before you start the solution or whatever. Power is force into velocity. This is simple, right? Power is force into velocity. Okay. Force in ideal drawing. Force in ideal drawing is Y bar AF ln A naught by AF. Remember, ln A naught by AF is also called capital R. So actually I have directly written this, but if you know, if you want to find the pressure, ideal pressure, then that pressure will be Y bar into ln R. Y bar ln R. That is the pressure. And when you multiply pressure by area, then you get the force. Pressure, when you multiply pressure by area, then you multiply. So this is it, right? That you see, you are doing the wire drawing. So the area is the area of the wire that you are drawing, and this is the equation. Now what is known? Is A naught known? Yes, no issue, pi by 4 d1 square. Is AF known? Yes, no issue, pi by 4 d2 square. So these two are done. AF is again the same thing as you just found. So Y bar is the only unknown, right? Y bar is the only unknown here. So Y bar we know is K epsilon N upon N plus 1. Do we know N? Do we know K? Yes. Now we know these values. Do we know epsilon? No, we have to find out. So we know that epsilon ln A naught by AF. When a cylindrical billet is changing area, cylindrical billet is changing from initial area to final area, then it is ln of A naught by AF. So you have already found A naught and AF. So epsilon 1 is now known. Remember, this is pi by 4 d naught square, pi by 4 df square. So pi by 4 cancel away. This can also be directly written as ln d naught square upon df square. But because we have already found areas already, therefore now you can do any way you like. So epsilon is now done. K and n are known. So you know all of this. So y bar is now known. And if y bar is known, all the other things were already calculated. Force is known. If force is known, velocity is given, then multiply force by velocity and power will be known. The only thing which you have to be always careful is that the units are the same everywhere. It is not that it is meter here and millimeter there, right? So write everything in the basic units. If something is in millimeter, write, for example, 8 millimeter, write 8 into 10 raised to minus 3. So it is already in meters. So the important thing always is that in every equation, you are using the same units. Then power will be directly given in watts and kilowatts and so forth, right? And finally, this will be, you see, this is the force in ideal drawing, and therefore this is the power in ideal drawing. If you remember, in extrusion and so on, sometimes we were giving you a direct formula for power, FL, N, this, that, in rolling and so forth. Sorry, in rolling. Here, the general formula that if you know pressure, multiply pressure by area and you get the force. If you know force, then multiply force by velocity, you get the power. This is general from earlier physics and so on. So here you have found the power for ideal work, and actual power will be 40% higher than that. So whatever power you found, you add, right, this plus 40% of this, or you write 1.4 multiply by this. So this is it, right? That rather than giving any formula or any calculation for the frictional and redundant work, we have used the formula only for the ideal work, but then the frictional plus redundant add 40% to it. So this is the solution of part A. Let us go to part B, where we were finding the die pressure at the exit and so on. So for die pressure, we have YF minus sigma D. YF minus sigma D. And sigma D or sigma is the same. The pressure at the die, right? So call it sigma D, whatever. And YF, right? Remember in the previous page, in the formula, it was Y bar, right? So there we used Y bar. This is simple Y. Y or YF. If you write Y, it is flow stress. If you write YF, it is flow stress. If you write Y bar, then it is the average. So here we have to recalculate. It is not divided by n plus 1, right? But otherwise it's simple. So YF or Y is K epsilon N. So you know K, you know N, you know epsilon, you just find the value. If it was Y bar, it will be divided by n plus 1 in the previous one, right? So that is why we are recalculating it, because it is only Y, not Y bar. And drawing a stress is just simple. Force upon area. Force upon area. Drawing a stress. A stress is a stress, right? A stress is a stress. So you have found that what was the force, right? You have found what was the force. Now remember, the force that you initially find was the ideal force. So multiplied by 1.4, this will be critical, because this is the actual operation, not the only the ideal part. That ideal part is only for doing calculation and so on. But the real one is ideal plus friction plus redundant total. So the total work is 1.4 times ideal work, or total work is 40% more than ideal work, right? So whatever force you found in part A, force, ideal force, multiply that ideal force by 1.4 to get the correct force, and then divide it by the area. So now if you have done that, then force divided by the area is drawing a stress. YF is this, put both of them here. This is the die pressure at the exit, right? So you have solved this question. And again, right, if you think and if you go back to the lectures and so on, wherever you have a confusion, then it is not something which is coming from a very unknown source, and so forth.